Welcome dear viewers, welcome to the course Quantum Chemistry. In this module, we are discussing about wave-particle duality, that is the dual nature of matter. Here we are focusing on wave-particle duality, the de Broglie relationship, applied potential and wavelength, matter waves and electromagnetic waves, a comparison between them, Davison-Germer experiment, which is the experimental proof to the dual nature of matter, and finally numerical problems. First of all, wave-particle duality. Isaac Newton thought that light consisted of corpuscles. Christian Huygens believed that light was a wave. By the end of 19th century, Thomas Young conducted a famous experiment known as Young's double slit experiment. And this experiment confirmed the wave nature of light. We can consider some important properties of light that may exemplify wave character and particle character. The first property is reflection, that is supported by the wave character as well as the particle character. Refraction is also an important phenomenon shown by light that is also supported by the wave as well as particle characters of light. Moving on to another optical phenomena that is called interference. Interference can be illustrated based on the wave nature of light. That is, particle property has no connection with interference. Another phenomena shown by light is diffraction. Diffraction can also be explained based on the wave property of light. Moving on to photoelectric effect that can be clearly explained by the particle nature of light. Thus, on comparing these properties shown by light, we can conclude that light can have a wave as well as particle character. Albert Einstein suggested this, that is, light has dual nature. That is, light can behave as both particle and wave. This dual nature is termed as wave-particle duality. Now, concept of matter waves. In the year 1923, Louis de Broglie proposed that matter, preferably electron, also have dual nature. The wave nature associated with the material particles are termed as matter waves, or simply matter waves are the waves associated with the material particles. Louis de Broglie won Nobel Prize for Physics in the year 1929. This is for his discovery of the wave nature of electrons. Now, we can move on to the famous de Broglie relation. The de Broglie relation is the relationship between wave property designated by wavelength and particle property designated by momentum p. The de Broglie relation is lambda is equal to h by p. We already know that p is equal to mass into velocity. Therefore, lambda is equal to h by mv. This relationship is known as the de Broglie relation. Now, we can derive the de Broglie relation. The de Broglie relation is derived from two well-known equations. Number one, Einstein's mass energy relationship. According to Einstein's mass energy relationship, energy related to velocity of light by the expression E is equal to mc square. I mark it as equation number 1. This is known as Einstein's mass energy relationship. Here, E represents the energy, m represents mass of the body, and c represents the velocity of light, that is 3 into 10 raised to 8 meter per second. Now, the second relation is Max Planck's quantum theory. According to Max Planck's quantum theory relation, E is equal to h nu. That is, energy associated with a wave traveling with the frequency nu can be calculated as E is equal to s nu. I mark it as equation number 2. On comparing left-hand sides of these two equations, we can see that left-hand sides are same and hence we can equate right-hand side. That is, mc square is equal to h nu. However, we know the fact that for a wave, nu is related to wavelength by the relation nu is equal to c by lambda. I can substitute this value of nu here. Therefore, I will get mc square is equal to hc by lambda. We can cancel one power of c from both the sides. Thus, we will get mc is equal to h by lambda. On rearranging, we will get lambda is equal to h by mc. It should be noted that c represents the velocity of light. An ordinary particle cannot travel with velocity that of light. Therefore, I am going to replace this velocity of light term with the small v, that is the velocity of the particle. Hence, this equation changed into lambda is equal to h by mv. We know the fact that mv is the momentum of the particle. Therefore, lambda is equal to h by momentum or h by p. This relation is known as the de Broglie relation. The significance of the de Broglie relation is that the particle property momentum is connected to wave property wavelength through a constant. That is, the constant is Planck's constant. And from this relation, it is clear that wavelength, that is the wave property, and momentum, that is the particle property, are inversely connected. That is, for particles having high momentum or high mass, the associated wavelength will be small and vice versa. Thus, we got the final relation, lambda is equal to h by mv. This is known as the de Broglie relation. Now, we are going to derive another aspect of de Broglie relation. Here, we are going to calculate the wavelength based on applied potential. Wavelength based on applied potential. This equation is derived to solve various numericals in which applied potential is given and asked to calculate wavelength. In that circumstance, we have to derive a mathematical relation connecting the wavelength of the electron with the applied potential. We can derive it like this. Consider an electron. The charge of an electron is small a, and charge is small a, and Let mass of the electron is small m. Let this electron move with a velocity v, and the applied potential is capital V. So, I am going to discuss the terms one by one. Consider an electron of charge small e. Let an applied potential of capital V is given to the electron. In that circumstance, electron will move with a kinetic energy. The kinetic energy of the electron under an applied potential of capital V is equal to charge multiplied by potential. Charge multiplied by potential. That is, kinetic energy of the electron is equal to small e into capital V. We know that if an electron is having mass m and velocity v, kinetic energy will be equal to half mv square. And hence we can write half mv square is equal to small e into capital V. Therefore, mv square is equal to 2e into capital V. See, this is small velocity, small v, that represents velocity. This is capital V, that represents the potential difference you are applying. And on this, v square is equal to 2e into capital V divided by m. And velocity of the electron v is equal to under root 2e capital V divided by m. I mark it as equation number 1. I am repeating the steps again for a thorough understanding. Consider an electron of charge small e. When we are applying a potential of capital V, it will get excited or it will get moved with a kinetic energy half mv square. And the kinetic energy of the moving electron under the influence of an applied potential capital V is equal to E into V. That is, kinetic energy is equal to small e into capital V. Half mv square is equal to EV. Moving in a similar simplified way, we will finally get the velocity of the electron as under root 2EV divided by m. And finally, we have the de Broglie relation, lambda is equal to h by mv. We can substitute the value of v in this equation. I mark it as equation number 2. Substituting equation 1 and 2, we will get the lambda is equal to h by m into value of small v. Small v is 2 into e into capital V divided by m. This is m raised to 1 and this is m raised to 1 by 2. So, a remaining term will be m raised to 1 by 2. M raised to 1 by 2 means root term. That root term enters into the denominator. Therefore, we get to the final relation lambda is equal to h by root 2 m e capital V. This is a very, very important relation that connect the applied potential and wavelength. That is, if you are applying V potential to an electron, it will move with a wavelength lambda. Wavelength lambda and applied potential V are connected by this relation. Lambda is equal to h by root 2 m e capital V. Capital V is the applied potential. Small e is the charge of the electron. You know the charge of the electron is 1.602 into 10 raised to minus 19 coulombs. This is the value of small e. And m is the mass of the electron, that is 9.1 into 10 raised to minus 31 kilogram. This is small m. And in this expression, the value of h is 6.626 into 10 raised to minus 34 joule second, known as the Planck's constant. So, we know all parameters except V. If you are knowing capital V or applied potential, just substitute in this equation, you will get to the corresponding wavelength value. Therefore, the relation between applied potential and wavelength is lambda equal to h by root 2 m e v. Now we can do some numerical problems based on the concept of de Broglie relation. First problem, calculate the wavelength of a body of mass 1 milligram moving with a velocity of 10 meter per second. Here mass is given, velocity is also given. We have to find out the wavelength of the electron. We can use de Broglie relation directly to find out the wavelength of the system. We know that as per the de Broglie relation, lambda is equal to h by mv. I mark it as equation number 1. And we know all the parameters in this equation. Mass m is 1 milligram. 1 milligram. 1 milligram means 10 raised to minus 3 gram. That means 10 raised to minus 6 kilogram. This is the mass of the body, 10 raised to minus 6 kilogram. Now, velocity of the body is given as 10 meter per second. I am transforming this milligram to kilogram since kilogram is the SI unit of mass. Velocity is already in meter per second, so no need for a conversion. And the Planck's constant value h is equal to 6.626 into 10 raised to minus 34 joule seconds. This is also in SI unit. Velocity is in SI unit. And mass is also in SI unit. On substituting all these values in equation 1, we will get to the wavelength associated with the system. That is, wavelength lambda is equal to 6.626 into 10 raised to minus 34 joule second divided by, and mass of the body is 10 raised to minus 6 kilogram. 10 raised to minus 6 kilogram multiplied with the velocity, that is 10 meter per second. 10 meter per second means 10 raised to 1. 10 raised to 1 into 10 raised to minus 6. So the denominator is 10 raised to minus 5. 10 raised to minus 5 cancels with the 10 raised to minus 34. So the final answer to the problem is 6.626 into 10 raised to minus 29. Since every quantities are present in the SI system, the unit is meter. This is the answer to the present problem. Now we can move on to other problem. A carriage moving with a speed of 100 meter per second has a de Broglie wavelength of 5 into 10 raised to minus 40 meter. The de Broglie wavelength is 5 into 10 raised to minus 40 meter. Calculate the mass of the carriage. We have to calculate the mass of the carriage. And we know the de Broglie relation, that is lambda is equal to h by mv. We have to calculate the mass of the system. M is equal to h by lambda v. We have to substitute the data. That is equal to value of h, that is 6.626 into 10 raised to minus 34 joule second divided by lambda, that is 5 into 10 raised to minus 40 meter multiplied with the velocity, that is 100. 100 is 10 square meter per second. We can simplify to get to the final value, and the final value is in SI system, and we will get answer in kilogram. On solving this, the final value is or 1.3252 into 10 raised to 4 kilogram. Here it is clear that mass of the body is very high and hence associated wavelength is very, very small or negligibly small. That means the wavelength associated with a macroscopic body is negligibly small. Now, we can do another problem in which wavelength to be calculated based on applied potential. Calculate the wavelength of an electron accelerated by a potential of 1000 volt. Since this is a relation connecting wavelength and applied potential, we have to use a modified form of de Broglie relation. That is, we have to use the relation lambda is equal to h by root 2 MEV. Here, in this equation number 1, h is Planck's constant, so I am putting the value as such, 6.626 into 10 raised to minus 34 joule second divided by, inside root we have to put some parameters, 2 into mass of electron, that is 9.1 into 10 raised to minus 31 kilogram, multiply with the charge of electron, that is 1.602 into 10 raised to minus 19 coulombs, multiply with the applied potential, that is 1000 volt, that is 10 raised to 3 volt. On solving this, we will get the lambda. Lambda is equal to 0.39 Armstrong. That is 0.39 into 10 raised to minus 10 meters. The value 0.39 Armstrong is a considerable value as far as the electron size is concerned. Hence, it is clear that the subatomic particle electron is associated with the substantial wave character. In the previous problem, we observed that for a macroscopic body, the associated wavelength is negligible. But for a microscopic system like electron, the associated wavelength is considerable. Now, we can move on to another interesting problem. The question is, what will be your wavelength? What will be the wavelength of the listener when you travel with a velocity of 1 meter per second? We are having a range of the wavelength of electron that appear in some angstroms. But now we are going to find out our own wavelength. By putting an arbitrary mass, we can calculate the wavelength. Each of you can calculate your own wavelength by putting your mass. That is, wavelength can be calculated by the same de Broglie relation, lambda is equal to h by mv. And for the sake of the calculation, I assume the mass of the body is 66.26 kilogram. This is mass of the body or mass of the individual. I am taking this value quite arbitrarily for the sake of doing the numerical problem easily. You can put your own mass in this place and find out the wavelength. And in the problem, it is specified that the velocity v is 1 meter per second. We can substitute these two values to get the wavelength. That is, wavelength lambda is equal to 6.626 into 10 raised to minus 34 divided by mass of the body, that is 66.26 into 1 meter per second. The numerator I can correct like this, 66.26 into 10 raised to minus 35 divided by 66.26 into 1 meter per second. These two terms vanishes and the wavelength is 10 raised to minus 35 meter. This value 10 raised to minus 35 meter is the wavelength associated with a person of mass 66.26 kilogram when that person travel with a velocity of 1 meter per second. You all having your own velocity, your own speed for walking, running, etc. You can take your own velocity, you can take your own mass, substitute these values in lambda is equal to h by mv to get your own wavelength. It is sure that your wavelength is definitely in the range of 10 raised to minus 35 meter. This means for a macroscopic body like us, the associated wavelength is negligibly small, or we can ignore the wave character. Moving on to another problem, that is comparison of wavelength of electron accelerated by potentials 100 volt and 1000 volt. That is, here we are going to find out the wavelength at applied potential 100 volt and applied potential 1000 volt. Lambda 100 volt is equal to h by root 2 me into 100. Lambda 1000 volt is equal to h by root 2 me into 1000. We can divide these two equations to get to the ratio. That is lambda 100 volt divided by lambda 1000 volt is equal to h vanishes, root 2 me vanishes, root 2 me vanishes, and root 1000 is in the numerator and root 100 is in the denominator. This is equal to 1000 is root 1000 is 10 into root 10 divided by root 100 is 10. We can cancel these 10s from numerator and denominator. Therefore, we will get to the final relation lambda 100 by lambda 1000 equal to root 10. Or finally, we can write lambda 100 volt is equal to lambda 1000 volt into root 10. This is a very, very important observation that we got from this problem. That all about the various numerical problems associated with the de Broglie relation. Now we are discussing difference between matter waves and electromagnetic waves. Matter waves, as we know, they are the waves associated with the matter. But electromagnetic waves are radiations having electric field and magnetic field with them. These are the differences between electromagnetic waves and matter waves. Electromagnetic waves are associated with electric and magnetic field. However, there is no significant field in matter wave. It can travel easily through vacuum. However, matter waves require some medium. They show high difficulty in propagating through vacuum. The electromagnetic radiations are emitted from sources in space. Existence is associated with the material particles in the case of matter waves. The speed of the wave is equivalent to the speed of the light. That is, every electromagnetic radiation travels with the velocity that of light. Speed is comparatively very less with that of light in the case of matter waves. Finally, examples. Radio waves, ultraviolet radiation, visible light, etc. are examples for electromagnetic wave, whereas electron beam represents a matter wave. These are the major differences between electromagnetic waves and matter waves. Now, we are going to discuss angular momentum postulate that can be derived from de Broglie relation. Here, the angular momentum postulate MVR is an integral multiple of h by 2 pi, or MVR is equal to nh by 2 pi. Angular momentum of an electron is an integral multiple of h by 2 pi is the Bohr angular momentum postulate. We can derive that Bohr angular momentum postulate from the simple de Broglie relation. Consider an electron moving in a circular orbit of radius small r around a nucleus. The wave is to remain continually in phase. That means the electron wave must be in phase within that orbit. Hence, the circumference of the circular orbit must be an integral multiple of the wavelength lambda. If the circumference is an integral multiple of the wavelength lambda, that wave can be very well fit in that orbit, or that wave is in phase with that orbit. In that circumstance, we can say 2 pi r is equal to n lambda, that is circumference of the orbit is an integral multiple of the wavelength of the electron wave. But we know lambda is equal to h by mv as per the de Broglie relation. On replacing lambda with h by mv, we can write 2 pi r is equal to ns by 2 pi. On rearranging, we will get mvr is nh by 2 pi, that is angular momentum of an electron in an nth orbit is an integral multiple of h by 2 pi, or simply mvr is equal to ns by 2 pi. This is the Bohr angular momentum postulate. Now, we are going to discuss experimental support to the de Broglie relation. It came from Davison-Germer experiment. De Broglie's hypothesis regarding wave character of electron received first experimental support from C.J. Davison and L.S. Germer. Their experiment is known as the Davison-Germer experiment. Regarding this experiment, electrons were emitted from hot filament and are accelerated by a potential between 40 volt and 68 volt before striking a nickel plate. That is, this electron beam is first accelerated by potential of range 40 to 68 volt and allowed it to struck on a nickel plate. This is the experimental setup. Heated filament produces electron beam. It is accelerated by an accelerating anode where the potential of acceleration is between 40 to 68 meter, which is optimized during the experiment. The electron beam allowed it to fall on the nickel surface. Then the electron beam will get diffracted at an angle theta. And Davison and Germer found that the impact of the electrons resulted in the production of diffraction patterns. The patterns are similar to those given by X-rays under similar conditions. That means electrons can also give patterns similar to that produced by X-rays. Since X-ray possess wave character, the experiment gave direct evidence for the wave character of electron as well. That is, Davison and Germer experiment offer experimental support to wave nature of electron or simply dual nature of matter. Thus, we have discussed various aspects about wave particle duality. That's all about this module. Thank you.